This video begins Missouri chapter 12. So the file in the physics 8/files web area is phys8 slides 12.pdf. The topic is torque. So we have been using for several weeks now Newton's second law, F equals ma, force equals mass times acceleration, or force equals inertia times acceleration. This basically tells you what force does. To find the acceleration of a given object, you take the force applied to it and divide by the inertia. So you could say acceleration is force divided by inertia, although the more conventional way to write it is force equals inertia times acceleration. The direct equivalent of that for rotation is torque equals rotational inertia times rotational acceleration. Just as we see the acceleration as the effect of a force and the mass as a constant of proportionality, we see the rotational acceleration as the effect of a torque, and the rotational inertia is a constant of proportionality. So the rotational acceleration equals the torque divided by the rotational inertia. Although, again, the more conventional way to write it is torque equals rotational inertia times rotational acceleration. Tau equals I alpha. So this is the Greek letter tau. It looks a little bit like the capital T you would see in Old English newspaper print. How do you produce a torque? The way you produce a torque is to apply a force at some lever arm from the rotation axis. So you take a force and you apply it some perpendicular distance, and perpendicular distance we learned in chapter 11 is also called lever arm. And the result of applying a force at some lever arm at some perpendicular distance from a rotation axis is a tendency to produce a rotation about that axis. Tau equals I alpha tells you the effect of a torque. It produces an rotational acceleration inversely proportional to the rotational inertia and directly proportional to the torque. Tau equals R perp times F tells you how a torque is produced. You produce a torque by applying a force at some lever arm with respect to the axis of rotation. This is a meter stick with a hole in it, and we have a little pin serving as a rotation axis sticking through the middle of the meter stick. And if I apply a force directly at the axis of rotation, it has zero lever arm. It has zero tendency to make this rod rotate. If I apply a force out here, which is about a quarter of a meter away, it has a very big tendency to make this meter stick rotate. That's the effect of lever arm. Now if I want to apply two forces with two opposite lever arms, a lever arm to the right and a lever arm to the left, so that they balance one another. Well, these are two copies of the same weight. So I can put them at the same distance on opposite sides of the rotation axis and they will balance. There's not much friction here, so I have to try pretty hard to make it balance exactly. Okay, after some adjustment, I made it balance pretty well. So you can see they're basically at the same distance, the same lever arm, the same perpendicular distance out from the axis of rotation, but in opposite directions. So one would tend to make it rotate clockwise, one would tend to make it rotate counterclockwise, and so they balance one another. I could try, this is a 200-gram mass. This is a 200-gram mass. Let's try replacing this one with a 500-gram mass. So we have 2.5 times as big a force. So to make them balance, I think I need a lever arm on this side, which is smaller by a factor of 2.5. So to make these two torques balance, I have a 0.25 meter lever arm on this side with a 0.2 kilogram mass, and I have a 0.1 meter lever arm on this side with a 0.5 kilogram mass. So this is 500 grams at 10 centimeters. This is 200 grams at 25 centimeters. And so in the product of this force times this lever arm equals the product of this force times this lever arm, and that balances the torques. If I move this out just a little bit, then we'll create rotation this way. Okay, this is a pretty heavy bicycle wheel, and I have a weight on a string here. It's a 200-gram weight on a string. And if I put the weight just a very small distance, like maybe about a centimeter out from the axle, it has some tendency, but a pretty small tendency, to make the wheel rotate. Now let's take that same weight and put it a much bigger distance out from the axle, and you can see it has a much bigger tendency to make the wheel rotate. It creates a much bigger angular acceleration. So watch this angular acceleration. And then watch this much smaller angular acceleration. And then here in between is an intermediate size angular acceleration, also known as rotational acceleration. Angular acceleration and rotational acceleration are synonyms. We say perpendicular distance because you see I could apply the force at a big distance from the axle, but this is a vertical displacement and a vertical force, so I get no torque. But if I apply that same vertical force at a big horizontal displacement from the axle, from the axis of rotation, which is the axle of this bicycle wheel, I get a big torque. So the perpendicular means if you're applying a vertical force, you have to count the horizontal distance between the axis of rotation and the line of action of the force. If you're applying a horizontal force, then you care about the vertical displacement, the vertical distance between the axis of rotation and the line of action of the force. And in general, you want to be careful to pick out the lever arm to be perpendicular to the force, or to use the component of the force which is perpendicular to the way you've drawn the lever arm. So the effect of a force is to produce an acceleration which equals the force divided by the inertia. The effect of a torque is to produce a rotational acceleration which equals the torque divided by the rotational inertia. And the way we get a force to produce a torque is we take that force and we apply it such that the line of action of the force passes some perpendicular distance away from the axis of rotation. So for example, if we wanted to apply two forces to this meter stick, let's suppose this is our meter stick and it is balanced through the middle, and I want to apply F1 at lever arm R perp 1, and I want to apply F2 at lever arm R perp 2, and suppose I want to apply these two forces in such a way that the two torques exactly balance one another so that there is zero tendency to rotate this meter stick about this axis, then I want to make sure that F1 times R perp 1 equals F2 times R perp 2. And of course I want one of them to tend to rotate clockwise and one of them to tend to rotate counterclockwise. We've been building up for a couple of weeks now this table of correspondence between what we learned about motion in a line or in a plane and what we're now learning about motion in a circle or about rotation. And so we now add the definition of torque. The effect of torque is to produce a rotational acceleration which is proportional to the torque and inversely proportional to the rotational inertia. And the way we produce a torque is to apply a force whose line of action passes some perpendicular distance, some lever arm, from the axis of rotation, or hypothetical axis of rotation. This idea of a lever arm actually occurred last week in chapter 11 when we saw how we can convert a linear motion into an equivalent rotational motion. So when we had the momentum of an incoming putty ball, for example, hitting a door at some perpendicular distance, some lever arm from the hinge, from the axis of rotation, that momentum times that lever arm produced an angular momentum. And now we see by complete analogy that a force applied some lever arm away from an axis of rotation produces a torque, which is a tendency to produce a rotational acceleration. I wind a string around a coffee can of radius r. Friction prevents the string from slipping, so the string is somehow wound around the can in a way that the string doesn't slip across the edge. It just unwinds as the can rotates. I apply a tension T to the free end of the string. The free end of the string is tangent to the coffee can so that the radial direction is perpendicular to the force direction. What is the magnitude of the torque exerted by the string on the coffee can? So that's something like this. So here the force exerted by the string is a purely vertical force, and then we want to measure the horizontal distance from the axis of rotation out to the point of application of the force. So we want to figure out where this vertical line of action of the force is perpendicular to this horizontal distance out from the axis of rotation. So we're going to measure horizontal distance, that's R perp, because it's a vertical force, F. And you can see the string is wound in a way that it doesn't slip, so if the can doesn't rotate, then the string doesn't go anywhere. But if we let the can rotate, then if the string goes down by one circumference, then the can goes around by one revolution. Using the numbers given in the problem, the tension in the string is 20 newtons, so that's the force, and the radius of the can is 5 centimeters, or 0.05 meters, so that's the perpendicular distance. So then the torque is R perp times F, which is 1 newton meter. So the units of torque are newton meters, because it's a force times a lever arm. Force in newtons times lever arm in meters is torque in newton meters. So here's the vertical force and the horizontal lever arm, which tends to create rotation this way. Right now I'm applying 2 torques to this coffee can. There's a second torque applied by my fingers, which is preventing any rotational acceleration. So if I release the torque applied by my fingers, then there's just the torque applied by the weight on the end of the string. So that's this force times this lever arm. And so you know, if we just have that one torque, or if we have, in general, if we have an imbalanced torque applied to the coffee can, then the result will be angular acceleration like this. And then, so suppose the angular acceleration of the can is 2 radians per second squared. You see I wrote 2 per second squared, but that's the same as 2 radians per second squared. When the string exerts a torque of 1 newton meter on the can, what would the angular acceleration of the can be if the string exerted a torque of 2 newton meters instead? So if we double the torque, then if it's the same can, it has the same rotational inertia. Angular acceleration is torque divided by rotational inertia. So if we double the torque without changing the rotational inertia, then we must double the angular acceleration. So if the angular acceleration with the 1 newton meter torque was 2 radians per second squared, if we double the torque without changing the rotational inertia, we should double the angular acceleration, so we should get 4 radians per second squared. So I think I like answer D, delta, an angular acceleration of 4 radians per second squared, because it's double the initial angular acceleration, which you should expect by doubling the torque without changing the rotational inertia. This next question says, I apply a force of 5 newtons at a perpendicular distance of 5 centimeters from this rotating wheel, and I observe some angular acceleration alpha. What force would I need to apply to this same wheel at a perpendicular distance of 10 centimeters instead of 5 centimeters to get the same angular acceleration alpha? We have here a wheel that can turn around, and then you see these funny arms spinning in the background. And actually attached to these funny arms, just out of sight, are 2 very big massive blocks, which tend to increase the rotational inertia of this contraption. So it's kind of like a big flywheel, has a pretty big rotational inertia. And then, this is a little bit like a bicycle's gear shaft. You have a 5 centimeter radius here, a 10 centimeter radius here, a 15 centimeter radius here, and just as a bicycle's chain can attach to a sprocket at different radii for different gears, we can apply a force by using a string wrapped around the 5 centimeter wheel, or wrapped around the 10 centimeter wheel, or wrapped around the 15 centimeter wheel, and it's causing the same mechanism to turn. So if we apply a given force, we can apply the force here and say what's that torque. We can apply the force here and say what's that torque. We can apply the force here, say what's that torque. Here's my half kilogram mass. So I'm going to apply 5 newtons at a distance of 5 centimeters, a displacement of 5 centimeters. And notice this force is downward and the displacement is horizontal. So the sine theta factor between the displacement and the force is 1. So it's just 5 centimeters times the tension in this string is the torque. So 5 centimeters, so actually 0.05 meters, right? So in newton meters, 0.05 meters times the tension in this string is the torque in newton meters that I'm applying with this mass. If this mass is not accelerating downward, if it's just hanging here, then the tension in this string equals mg, which is 5 newtons. If I let go of this and it starts accelerating, then technically the tension in this string is no longer mg, it's mg minus ma, where a is the downward acceleration. You have to bear that in mind, but to keep things simple, let's pretend it's mg rather than mg minus ma. And that actually is not a bad approximation, because you're going to see that this thing doesn't accelerate downward anywhere near g. So let's just say it's mg, even though we know it's mg minus ma. Now capture in your mind's eye how big is the angular acceleration? So that means like how fast it goes around and faster and faster and faster. And how often it goes around is the angular velocity. The rate of change of how often it goes around is the angular acceleration. So you're going to see it go around and around and around faster and faster. That's the angular acceleration due to this torque. Okay, let's watch that. Okay, now I want to try to get that same angular acceleration, and it's the same flywheel, but I want to get that same angular acceleration by applying a force at 10 centimeters instead of applying a force at 5 centimeters. This was a 5 Newton force. So how big a force do I have to apply at 10 centimeters to get the same torque and therefore to get the same angular acceleration? 0.05 meters times 5 newtons is the same as 0.10 meters times 2.5 newtons. So instead of 5 newtons, I want 2.5 newtons. And the way I get 2.5 newtons is instead of using a 500 gram, half kilogram block, I'll use a quarter kilogram block, a 250 gram block. We now have a 2.5 Newton force at a lever arm of 0.1 meter. So we should get the same angular acceleration we got last time. Let's see if it looks the same. For comparison, well, let's see what happens if we apply that 2.5 Newton force at the original 0.05 meter displacement. Now, do you expect a bigger or a smaller angular acceleration? This is half the torque, but the same rotational inertia, so I think we'll see half the angular acceleration we saw before. Let's see what that looks like. One more data point. Let's put the 5 Newton force at the radius at the displacement of 10 centimeters, 0.1 meter. So now we have at a lever arm of 0.1 meters, we have a force of 5 newtons. So this should be twice as large a torque as we had when we had the 2.5 Newton force at 0.1 meters. So this should be the biggest angular acceleration we've seen yet. Let's see. Okay, since we haven't changed the rotational inertia, to get the same angular acceleration, we would have to apply the same torque. I applied a force F1, which was 5 newtons at a perpendicular distance. Our perp1 was 5 centimeters from the center of the wheel. So if I want to get the same torque at a distance of 10 centimeters instead of 5 centimeters, so I've doubled the lever arm, so I want to cut the force in half to get the same torque. So you can see going from the original torque to the new torque, I have doubled the lever arm. So if I have twice the lever arm, I want half the force to get the same torque. So if I initially applied 5 newtons at 5 centimeters, instead I should apply 2.5 newtons at 10 centimeters to get that same torque. And then for the given rotational inertia, that should be the same angular acceleration. So the original torque that I applied was 5 newtons at a lever arm of 0.05 meters. So that gave me 0.25 Newton meters. To get the same torque and therefore the same angular acceleration using a lever arm of 0.1 meters, I have to apply a force of 2.5 newtons. So if I double the lever arm, I cut the force in half to get the same torque, and that same torque will give me the same angular acceleration, assuming that it is the same rotational inertia. Suppose I use the tension T in a string to apply a given torque, which is R perp times T, to this wheel, and the wheel then experiences a given angular acceleration alpha, also known as a rotational acceleration alpha. Now I increase the rotational inertia of the wheel. How am I going to do that? Well, this particular wheel has some adjustable masses, and they're positioned symmetrically, and so I can put them both in close to the axis, or I can put them both far away from the axis. And by doing that, that mr squared factor increases or decreases the rotational inertia of this big wheel. Somehow I'm moving the mass closer to the axis to reduce the rotational inertia, or I'm moving the mass farther away from the axis to increase the rotational inertia. So I increase the rotational inertia I of the wheel and then apply the same torque. The new angular acceleration will be, well, angular acceleration is torque divided by rotational inertia. So if you keep the same torque, but you make the rotational inertia bigger, then you expect a smaller angular acceleration. So I like answer C, Charlie. The new angular acceleration will be smaller than the original angular acceleration. because we applied the same torque to a system that had a bigger rotational inertia. So that's a smaller angular acceleration, smaller rotational acceleration. So this is the angular acceleration we get with a 5 Newton force at a displacement of 0.1 meter. Now, let's apply that same force at that same displacement, so it's the same torque, but let's find a way to substantially increase the rotational inertia of this device. Same force, same displacement, therefore same torque, but we have dramatically increased the rotational inertia of the red wheel by putting these big masses out farther from the center. Let's see what the angular acceleration is now. Oh, that's really pretty slow. Okay, so this is illustrating that torque equals the product of rotational inertia times angular acceleration. So just as acceleration is force divided by mass, we have angular acceleration as torque divided by rotational inertia. Here's an example reading question I've used for a while. I want to tighten a bolt to a torque of 1 Newton meter, but I don't have a torque wrench. A torque wrench is a wrench which applies a known torque. I do have an ordinary wrench, a ruler, and a 1 kilogram mass tied to a string. How can I apply the correct torque to the bolt? Well, let's suppose I orient the wrench horizontally and I hang the mass at a distance of 0.1 meter from the axis of the bolt. Let's try that. So if I put this mass a distance of 0.1 meter from the axis of the bolt. I guess I drew a nut here, but our perpendicular is 0.1 meter. And then if it's a 1 kilogram mass, then that's a force of about 10 newtons. Let's say 9.8 newtons. We can round it to 10. So it's 10 newtons times 0.1 meter. That seems like a torque of 1 Newton meter. So I think this should do the job, although I'm neglecting the fact that the weight of the wrench itself is applying an additional torque. So I suppose to do this, I would have to do it with a wrench which is much, much less massive than this weight that I'm hanging here. Or somehow I would have to correct for the torque due to the weight of the wrench. And actually that would be the center of mass of the wrench. So I say how far out from this axis is the center of mass of the wrench, and then I can multiply that lever arm by the weight of the wrench, and that would be an additional torque in the same direction. If we take the center of mass of the wrench, then there's an additional torque, which is the mass of the wrench times G is the force, and then there's the distance from the bolt axle to the center of mass of the wrench. So I suppose in the original question statement, I was assuming that this additional torque due to the weight of the wrench times the lever arm from the center of the bolt to the center of mass of the wrench was negligible, but it may not be. So if it is, then I suppose you would move the point of application of this additional mass in so that the sum of those two torques is a desired torque. But let's suppose we do this with a wrench that on its own has negligible mass. So then we do just want to apply our 10 Newton 1 kilogram mass times G is about 10 newtons. We want to apply our 10 Newton force, a lever arm of 10 centimeters, 0.1 meter from the bolt axle to give us a 1 Newton meter torque going this way. So I like answer A. If you got answer B, you might have forgotten to include the little g to convert the mass into the weight. And of course you want the force, which is mg times the lever arm. The torque is the force times the lever arm. The force, in this case, is the weight, not the mass, but the weight. So the weight is the mass times little g. And then we take that weight and multiply it by the lever arm, and that gives us a torque. Suppose now that the same wrench is at a 45-degree angle with respect to the horizontal, but we still have this 1 kilogram mass, and it is still a distance of 10 centimeters, 0.1 meter, from the bolt axis. So it's suspended at a distance 0.1 meter along the wrench. Will it still exert a torque of 1 Newton meter on the bolt? Or as I've drawn it here, a nut instead of a bolt. Well, you could say, gee, the force of gravity hasn't changed and the distance hasn't changed. Maybe it's the same torque. Or you could say, well, no, I think the torque is now larger. Maybe it's larger by a factor of the square root of 2. Or you could say, gee, maybe the torque is now smaller. Let's say maybe it's smaller by a factor of the square root of 2. Well, I think it's the same force, but the perpendicular distance. How is it the same or has it changed? I think instead of wanting to use the whole distance, now we want to use just the perpendicular part of the distance, the part of the distance which is perpendicular to the line of action of this force. Since this is, well, it's a string hanging, but it's basically hanging vertically, so this is a vertical force, so we want the horizontal distance to go with the vertical force. So we want to pick out just the horizontal part of this distance, and that horizontal part of this distance goes with this vertical force. So I think we're going to get a smaller torque. Let's see how much smaller. So in this case, my distance d was 0.1 meter, and my force, mg, the tension in the string, which in this case is just mg, is 10 newtons. But I don't want the whole distance. Our perp here, the perpendicular distance from the axis of rotation to the line of action of the force, is just the horizontal part of this displacement. It's not the entire displacement. Since I have a vertical force, I want the horizontal displacement. So I can pick out the horizontal component of this displacement by drawing a triangle here, and I say, aha, I must want this distance times the cosine of this angle with respect to the horizontal. So that's the distance times the cosine of 45 degrees. The cosine of 45 degrees is 1 over the square root of 2, which is about 0.71. So it seems like our perpendicular is about 0.71 times this 0.1 meter distance. So my torque will be r perpendicular times the force. R perpendicular is just d over root 2, which is 0.071 meter, right? So I take 0.1 meter and I multiply it by this factor of 0.71, and that gives me 0.071 meters. The force is still 10 newtons, so 0.071 meters times 10 newtons is 0.71 newton meters. So I think I like this, 0.71 newton meters. One thing to bear in mind about this diagram that's pretty tricky is we wanted to pick out the horizontal component of this force, and this theta was measured with respect to horizontal, so we used the cosine of this angle. But bear in mind that the cosine of this angle is the sine of this angle. So this angle that we drew as theta is the angle between the actual displacement vector and the horizontal, because we knew we wanted to pick out the horizontal part. But we could have asked, what is the angle between the line of action of the force and the displacement? So that angle between the line of action of the force and the displacement vector is actually this angle that we didn't label. I don't really want to label it right now because we'd have to choose a symbol to label it with, and I'm not sure what symbol to choose. But bear in mind that because we have a right triangle here, the cosine of this angle down here equals the sine of this angle up here. And this angle up here is actually the angle between the force vector and the displacement vector. So it's actually more common to consider the angle between the force vector and the displacement vector. Although in this particular case of the wrench problem, we knew we wanted to pick out the horizontal part of the displacement because the force is vertical. We know that a vertical force will go with a horizontal displacement. So we drew the angle here so that it would be easy to pick out the horizontal component. In general, if you have a force and a displacement at some arbitrary orientation, then you want to ask yourself, what is the angle between the force and that displacement? So suppose we have the more general case where the vector from the axis of rotation to the point of application of the force is not perpendicular to the force. So here I've drawn the line of action of the force in blue, and I've drawn, and here up at this intersection point is the point of application of the force. And then here's my rotation axis. And I've drawn this vector r from the rotation axis to the point of application of the force. So if we want to get the magnitude of the torque due to applying this force at some non-zero lever arm here, we have several ways to do it. The first way, which we've been using, is to pick out the perpendicular component of this displacement, r. So since it's a vertical force, we want to pick out the horizontal part of r. Another thing we could do is, since we have this displacement vector in this direction, we could pick out the perpendicular component of the force. Now in this case, since the force is drawn as a vertical line, it's easy to pick out the horizontal part of the displacement. Sometimes the displacement is horizontal and you have a diagonal force, so then it's pretty easy to pick out the vertical part of the force. Or sometimes you have a purely vertical displacement and you have a diagonal force, so then it's easy to pick out the horizontal part of the force. So if either the force or the displacement is naturally along some easy to use axis, then often it's easier just to pick out the perpendicular component of the other one. So if you happen to have a nicely vertical force, you can just pick out the horizontal displacement. If you happen to have a nicely horizontal displacement, you could just pick out the vertical part of the force. In general, there's some angle theta between the displacement vector r and the force F. If these were perpendicular to one another, then that angle theta would be 90 degrees. So if the angle theta is 90 degrees, the sine of 90 degrees is 1. So ideally, you would like this displacement vector and this force vector to be perpendicular to each other, and then multiplying by the sine of this angle is just multiplying by 1. So we can say the torque, the magnitude of the torque, is the perpendicular part of the displacement times the force. In this case, the perpendicular part of the displacement would be picking out this component like that, or we could pick out the perpendicular part of the force like that, or we can take the entire displacement magnitude times the entire force magnitude times the sine of the angle between the displacement and the force. And again, we use the sine to pick out the perpendicular part. Remember, when we did the dot product, we were using the cosine to pick out the parallel part. In this case, we're using the sine to pick out the perpendicular part, and that's because, in exact analogy with our expression involving the cross product for angular momentum, there's actually an expression for torque, and we actually later we'll see torque as a vector. So torque as a vector is the displacement vector cross product with the force vector. And if we take the magnitude of the torque, then it's the magnitude of this cross product. And the magnitude of this cross product is the magnitude of this vector times the magnitude of this vector times the sine of the angle between them. So 4 ways to get the magnitude of the torque. We can take the perpendicular component of the distance times the entire magnitude of the force. We can take the entire distance times the perpendicular component of the force. We can take the entire distance times the entire force times the sine of the angle between the displacement and the force. Or equivalently, we can take the magnitude of the vector product r cross f, which is also called the cross product. So there's this thing called the vector product or the cross product. You calculate it using the right hand rule. My right hand looks like a left hand with the light board flipped. So that's 4 different ways to calculate the magnitude of the torque. You can use whichever one is most convenient for a given situation. To tighten a bolt, I apply a force of the same magnitude F at several different positions and angles. In which case do I get the largest torque? It seems like in case F, I am using the entire distance and the force is perpendicular, so the sine theta factor is 1. So this is the entire length of the wrench times the force, and the sine of 90 degrees is 1 since they're perpendicular. So I think I get the entire F times the entire distance in this case. Actually, this seems to be clearly biggest because there's no place else that I'm implying the force at the entire length of the wrench. So here I'm using it's perpendicular, but it's a smaller distance. Here it's perpendicular, but it's an even smaller yet distance. And it seems like C and D are the same magnitude, but in opposite senses. So one is clockwise and one is counterclockwise. And then if we look at A and B, in both cases the force is applied at an angle. So if we have a horizontal displacement, see here's a case where we have a horizontal displacement, so it would be convenient to pick out just the vertical part of the force. So to get the torque, we have the horizontal displacement times the vertical component of the force. Here we have the horizontal displacement times the vertical component of the force. So it seems like B would actually be a smaller torque than D because the distance is the same, but we only get a portion of the force for B, whereas for D we get the entire force. I think C and D would be the same magnitude but opposite directions. And then E is a small displacement but the entire force. A is that same displacement as E, but it's even a smaller, effectively a smaller force because we only get the vertical portion of the force. In any case, this question is saying which torque is largest. So I think it's clear that situation F, Foxtrot here, situation F has the largest largest torque because it's the entire force, because it's perpendicular, and it's the entire length of the wrench. So I like F for the largest torque. Now in this case, which torque is smallest? It seems like the smallest displacement from the axis of rotation is like a tie between A, alpha, and E, echo. However, here the force is perpendicular to the displacement. Here the force is at a funny diagonal angle. So we actually not only have a small displacement for A, but we also have to pick out only the vertical component of this force. So I think A, alpha, is the smallest torque because not only is it a small distance from the axis of rotation to the point of application of the force, but because the force is not perpendicular to the displacement, we get only the perpendicular portion of the force, which is smaller than the entire force. I want to apply to this meter stick two torques of the same magnitude in opposite sense. In other words, one clockwise, one counterclockwise, so that the stick has zero rotational acceleration. I apply one force of 5 newtons at a lever arm of a half meter. So here's a half meter. This is a meter stick. Here's a half meter, and this is half a kilogram. So using G is about 10, that's 5 newtons. And you can see the hole in the stick isn't quite all the way at the end because you can't put a hole all the way at the end, but it's pretty close to half a meter. I want to apply an opposing force at a lever arm of 0.2 meters. So there's 0, 0.1, 0.2, so that the second torque balances the first torque. How large must this second force be? Well, I think you want horizontal distance times vertical force equals horizontal distance times vertical force. So if this is 5 newtons at a half meter, then this is 2/5 the distance, so we must have to have 5 halves the force. So that's 5 times 5 over 2 is 25 over 2 is 12.5. So I think we need 12.5 newtons. In fact, this is 1.2, 1.25 kilograms. So I put 1.25 kilograms over here, I put a half kilogram over here, and they balance. And to convince you that I had to make them balance, I could, well, if I remove this, you see they don't balance and it starts to tip over. To repeat, we put a 5 Newton force perpendicular at a perpendicular distance of a half meter, and that gave us a 2.5 Newton meter torque. In the other direction, we put a 12.5 Newton force at a perpendicular distance of 0.2 meters. That gave us a 2.5 Newton meter torque. So these two torques about this axis of rotation balance one another because one tends to go this way, one tends to go this way. They have the same magnitude in opposite sense, so the meter stick was balanced. So I want to apply to this meter stick two torques of the same magnitude in opposite sense so that the meter stick has zero rotational acceleration. I apply one force of 10 newtons at a lever arm of a half meter. So this is a vertical force of 10 newtons at a horizontal lever arm of a half meter. I tie a second string on the opposite end, a half meter from the pivot point. The pivot point is in the middle here, so this is a half meter horizontally, this is a half meter horizontally. But now the second force is applied at an angle which is 45 degrees away from the vertical. How large must this second force be? Well, one way to analyze this would have been to say, let's take the line of action of the force and extend it until it's perpendicular, and then figure out the smaller r perp. You see, we could extend the line of action of this force, and then at some point we would be perpendicular, and we could measure the perpendicular distance. That turns out to be inconvenient for this problem because we know the displacement is horizontal. So we really just want to pick out the vertical part of this force to get the torque. So we could have extended the line of action up to here and said, oh, this is r perpendicular. But that turns out to be inconvenient for this problem. Instead, we want to say, let's just pick out the vertical part of this force. And the vertical part of this force, in this case, since it's a 45-degree angle, is just this force divided by the square root of 2, which is the force divided by 1.414. So we only get a fraction 1 over 1.414 of the force. So in order to balance, it's the same distance. So in order for this torque to balance, it's the same horizontal distance, but this is a perfectly vertical force. This force is at a funny angle, so we only get 1 over root 2 of the force that we apply. So in order to get the same torque, we have to apply a force which is bigger by a square root of 2. So this second force has to be a square root of 2 bigger than the first force. So we need to apply a force which is bigger than the left-hand force, bigger by a square root of 2, so we need to apply a 14.1 Newton force instead of a 10 Newton force, since we only pick out the vertical part. So if the magnitude of this force is 14.1 newtons, then the vertical component of it will be 10 newtons, and these torques will balance one another. So I like answer D, delta, for this question. We have 10 newtons downward at 0.25 meters, so that's a clockwise sense. And then we'll have an unknown force upward, so that'll be a counterclockwise sense with respect to this pivot. Unknown force at 0.5 meters, so if this is 10 newtons, how big will this unknown force be so that the torques balance? Let's see. Okay, 5 newtons. So 5 newtons at 0.5 meters balances 10 newtons at 0.25 meters. So this will still be 10 newtons downward at 0.25 meters. Now what if we apply this force at a 45-degree angle? How big does the force then have to be? If I'm holding everything just right, then you should get about 7 newtons. You want the upward component of this force then to be 5 newtons. And so if the force goes this way, the upward component is this force times the sine of 45 degrees. If this rod doesn't accelerate rotationally about this pivot, so here is a pivot, and then we go out, and this is the point of application of the force, and I hang a 1 kilogram mass here. So 1 kilogram of M gives me mg equals 9.8 newtons. Let's call that 10 newtons. So we have 10 newtons down. What force do I have to apply up to balance it? So this 10 newtons down gives me a clockwise torque. So I want a clockwise torque upward of the same magnitude. It's actually at the exact same lever arm, so I guess it just has to be 10 newtons up. So I have 10 newtons up, 10 newtons down applied at the same lever arm. Those two forces, those two torques balance. So D, delta, I only need 10 newtons here because I have 10 newtons downward. That gives me a clockwise torque. Then I have 10 newtons upward. That gives me a counterclockwise torque, and they balance one another. So I have my pivot, and half a meter out from my pivot, I have a 1 kilogram mass. That's a downward force of 10 newtons. The second force I'm going to apply is at the same distance. This tends to accelerate clockwise. This will tend to accelerate counterclockwise. So how big will this force be to make the torques balance? Did you say 10 newtons? Good. Okay, now I have, here's the pivot way on the left, and halfway across the ruler I have an unknown force which is upward. Then all the way across I have a 10 Newton force which is downward. So 1 kilogram times little g is 9.8 newtons. We'll call that 10 newtons. So we have 10 newtons downward. Now a downward force would tend to be a clockwise rotation, and an upward force here would tend to be a counterclockwise rotation if the tendency is to rotate about here. So here we're rotating clockwise about the pivot with this downward force, and this upward force is tending to produce a counterclockwise or anti-clockwise rotation about the pivot. So the typical convention that we use is anti-clockwise minus clockwise. So the counterclockwise torques we do with a plus sign, the clockwise torques we do with a minus sign. You could use the opposite convention if you want, it's just nice to have a convention. So we see we draw this little anti-clockwise arrow, kind of a curved arrow. That's saying our convention is, our sign convention is that we're going to be counterclockwise about this pivot. So this is an unknown force up F at a lever arm of L over 2, and then here is a 10 Newton force at a lever arm of L, and this has a minus sign because it is clockwise, this has a plus sign because it is counterclockwise about this pivot. You see, if we pivot about here, this force would tend to make a anti-clockwise rotation, this force would tend to make a clockwise rotation. So in order for these two things to sum to 0 so that the rod doesn't accelerate, then we need this unknown force to be 20 newtons. So I think I like answer F, Foxtrot here, 20 newtons. So we have 10 newtons at 0.5 meters. We have an unknown number of newtons at 0.25 meters. How many newtons will this be? How about 20? Okay, now we basically reversed the position, so we want to balance the two torques. So here's one clockwise torque about this pivot, and here's one anti-clockwise torque about this pivot. So we're using the convention that anti-clockwise is positive, so we'll do positive minus negative. So this is a lever arm of L times an unknown force F upward. This is a lever arm L over 2 times a known downward force 10 newtons. So we'll do positive minus negative, anti-clockwise minus clockwise, lever arm L times force F minus lever arm L over 2 force 10 newtons. So F must be 5 newtons. So I think I like answer B, bravo here, that the force must be 5 newtons. So 5 newtons times L is the same magnitude as 10 newtons times L over 2. This one tends to rotate counterclockwise, this one tends to rotate clockwise, so they have opposite sense. Okay, now we're again applying two forces. They result in two torques. We want the two torques to balance so that the rod does not accelerate. Here's the pivot point. Our convention, again, will be counterclockwise is positive. Here's a lever arm of L over 2. L over 2 horizontal lever arm, 10 Newton vertical force, that's clockwise. Now we have a lever arm of L, but this force is applied at a 45-degree angle, so we only get to pick out the vertical part. So if this is magnitude F, the vertical part is F divided by square root of 2. And this would tend to rotate counterclockwise, that's our positive sense. So we pick out the vertical part of F, that's F over root 2, and then the distance is L. That's positive because it's counterclockwise. Then the clockwise part is 10 newtons, L over 2. And those should sum to 0. So I think this force that we apply here has to have magnitude 10 newtons divided by root 2, which is 7.1 newtons. See, the vertical part has to be 5 newtons. Since this has twice the lever arm, this is 10 newtons down, so 5 newtons up at twice the lever arm would balance, but 5 newtons up is the same as 7.1 newtons at a 45-degree angle. So the force that we need to apply is 10 newtons times root 2 over 2 is 7.1 newtons, because this anti-clockwise positive torque is F over root 2, that's picking out the vertical part, is F over root 2 times L, and then this clockwise part is 10 newtons at a lever arm of only L over 2. So those two terms balance one another. That gives us the magnitude of F, which we apply diagonally, is 7.1 newtons. That looks like roughly 45 degrees. So if I'm holding everything just right, then you should get about 7 newtons. Okay, so we're again pivoting about this left end of the meter stick, and we have a downward force of 10 newtons applied at a lever arm of L over 2. So this is horizontal distance L over 2, vertical force 10 newtons, clockwise sense. And we want to balance it with a counterclockwise torque. So here we are applying the force at the full length of the meter stick, that's L, but now we're making a 30-degree angle with respect to the horizontal. So we want to pick out just the vertical part of this force. So this is F perp. See the part of the force which is perpendicular to the displacement, and that would seem to be F sine 30 degrees. So the displacement is horizontal, so we want just the vertical part of the force. This is F. The vertical part of F is F sine 30 degrees. So we'll do anti-clockwise minus clockwise. So this is F sine 30 degrees times L minus 10 newtons times L over 2. Horizontal displacement times vertical force, horizontal displacement times vertical force. Anti-clockwise is positive, clockwise is negative. Sine of 30 degrees is a half. So this is F times a half times L minus 10 newtons times L over 2. So that works out if the force is 10 newtons. So I think I like D, delta. The force is 10 newtons. So it turns out that angular momentum is a vector, and it turns out that torque is a vector. And you might wonder, how do you associate a vector in space with something which is rotating or tending to cause rotation? Well, because we live in three-dimensional space, when something rotates, rotation really takes place in a plane. So there's some plane in which everything is rotating here. And if I tend to cause something to rotate, all of that rotation happens in a plane. But it's convenient to use the vector perpendicular to that plane of the rotation to represent the rotation itself. And that works because we're in three-dimensional space. So really, rotation is represented by a plane, because when you make something rotate, you're rotating things within a plane. But in three-dimensional space, we have the convenient option of using the vector perpendicular to that plane to represent the plane of rotation. Now that still leaves us a sign ambiguity. So you can say that the motion of the hands of a clock clockwise can be represented by an axle which is perpendicular to the face of the clock. But then you say, well, is the motion of the clock the arrow that points into the board, or is it the arrow that points out of the board? And the convention is that the motion of a clock is the arrow that points into the face of the clock. Now this is actually my right hand, although I mirror the video for the light board, so it looks to you as if it's my left hand. But using my right hand, if I wrap my fingers of my right hand around in such a way that my fingers are pointing the way the clock hand moves, then my thumb points into the plane of the board. So see if you can do that with your right hand. I know it's a little confusing because I mirror the video, but if you twist your fingers around so that your fingertips are pointing the way the hands of a clock move, then you'll find that your right thumb points into the plane of the clock. So the vector that we use to represent clockwise motion points into the face of the clock. If we have a vector, let's say this is R and this is F, and let's say this is R and this is F, then we take R cross F with the right hand. So you start out with the fingers of your right hand moving along the R vector, the displacement vector, and then you curl the fingers of your right hand so that they subsequently point in the direction that the force is pointing. And then you ask, which way is your thumb pointing after you're able to do that? And in this case, my thumb is pointing out of the plane of the board. So I take a vector to the right, cross product with a vector up, and it gives me something that points out of the plane of the board. By contrast, if I take a vector that points to the right and I do the cross product with something that points down, then my thumb points into the plane of the board. This is using my right hand, although it looks like a left hand to you. So this is R cross F, and it points into the plane of the board. So the convention is, now you know that this would be a clockwise torque, and you know that this would be a counterclockwise torque. So a counterclockwise torque by convention points out of the plane of the board. A clockwise torque by convention points into the plane of the board. That's the so-called right-hand rule. Almost every screw or bolt that you pick up, except for certain screws that are made backwards for safety reasons, almost every screw that you pick up will have right-handed threads. So that means if you turn in a clockwise way, the bolt will move away from you. So when you tighten a nut or a bolt by turning clockwise, that bolt tends to move away from you. And if you move counterclockwise, then the bolt will tend to move toward you. That is a right-hand threaded bolt or screw. It's possible to manufacture bolts or screws the other way, but the convention is that 99.9% of bolts and screws have right-handed threads, meaning that if you turn in the direction that your fingers of your right hand curl, then the screw or bolt will move in the direction of your right thumb. Try that out and check it out the next time you have a bolt or a screw in your hand. There are a few examples of places where screws or bolts are threaded the other way, and sometimes it has to do with safety mechanisms on things that rotate, like rotating pieces of machinery. Sometimes there's a desire to make things deliberately incompatible, so you don't thread incompatible things to each other, so one of them will be made left-handed threaded so that you can't accidentally connect it to something which is maybe more common but incompatible. If you look at the face of a clock whose hands are moving clockwise, do the rotational velocity vectors of the clock's hands point toward you or toward the clock? Well, they point toward the clock. I'm looking at the clock, they point toward the clock. So the clockwise direction is into the plane of the board by convention. So we're actually reaching a really interesting and important and fun part of the course. We're going to see, now that we have, remember at the beginning of the course, Professor Farley told us that in order to look at structures, we need first to have three things under our belt. We need to understand forces, vectors, and torque. So we did forces when we got to chapter 7 of the textbook. We did vectors when we finally got to motion in a plane and we learned how to decompose forces on an inclined plane, for example, into their components. And now finally we're getting to torques, and we're just getting our feet wet with torques. But pretty soon we'll understand torques and how to use them. So torques are important in architecture because they allow us to determine the conditions for a structure to stay put. So for an object like a structure or a part of a structure to stay put, it must have zero acceleration and it must have zero rotational acceleration. So you don't want a piece of a building to accelerate, and you also don't want a piece of a building to accelerate rotationally. So the vector sum of all forces on a structure or a part of a structure must add to zero, and the sum of all torques about any axis using the appropriate sign convention must also be zero. So then you keep the acceleration is zero for every part of a structure, and you keep the rotational acceleration zero for every part of a structure. If these conditions are met, the object is in equilibrium. That means there are no unbalanced forces and there are no unbalanced torques. So writing the conditions for equilibrium is a fundamental part of analyzing structures. So we will spend a lot of time doing that. So that will be the next thing that we do when we pick up and move ahead using our understanding so far of forces and torques and vectors. Right now, it's Halloween. It just became dark out. I'm going to go outside and hand out Halloween candy to the neighborhood kids. So this is the end of this video segment, and we will pick up next weekend and continue with the really cool and fun application of torque to things that have to stay put so that they can hold other things up.